Okay, calculus people, this is the end of our notes on section 9.3. We're going to finish up the two examples we didn't quite get to today in class. That was on Friday the 13th. And yeah, see if we can't show you the shortcut for how to do this stuff much, much quicker on the calculator. So this is the example we left off on here. We did it pretty much the same way in both classes, and this is how we would have done so back in the old days, kind of where we did everything by hand. But with the stuff that the Inspire can do for us, we're going to make this go a lot faster here in the future. By the way, first hour people, I don't know if I told you guys, this right here, everybody, is a notation that the book starts using in this section. The y with the dot over the top, and as you might have guessed, that's just another way to express the derivative of the function. So it's a diffie-q, so the derivative of y with respect to x is that 0.5 minus x. Okay, on to example B here. So again, as is the case with all Euler's method problems, we've been given three things, everybody. We have our differential equation right here. We have our initial condition, which we'll eventually be expressing as an ordered pair right here. And then we have the value of dx, the size of the step that we're going to take in each one of these problems. Now, if you take a quick look at where we're starting, we're beginning with the ordered pair -2, -3.4. Our directions here are to approximate the value of y1. So that means that in going from here to here, if you take a look at those x values, we've got to go a total jump of 3 units from x equals -2 to x equals 1, and to do so with a step size of 0.3. So that 3 divided by 0.3 means that we have to take 10 steps. And if I was going to write everything out by hand the way we did back here in example A, this one only took 3 steps, but we're going to need 10 on this one. You can see how this would take a while. So let's talk about how we can cheat just a little bit and do this a lot faster on the calculator. So I am going over here to the Inspire. I opened up a brand new document because we're actually going to need, I think, at least 3 and maybe a 4th page open just for fun. So I'm going to begin with a calculator page. And the first thing we are going to do, everybody, is to define our differential equation. Now, we usually just call our functions f1 of x. But since our differential equations can be defined in terms of either x or y or both, I'm going to go ahead and define this as a 2-variable function, which we've done occasionally during the course of the year. And in this example, the derivative that we're going for is y minus the cube root of y. So we're going to type that in as y minus, and we'll go over here and put in a cube root of y, and hit enter, and everything is hunky-dory. That is the only thing we need to do off the calculator page. Most of the work we're going to do now comes from a list and spreadsheet, which we did a little bit back in the first semester. So I'm going to hit Control and add a page, and then go to number 4 here for lists and spreadsheets, and click right there. As we did before, it's going to help later on to know what it is that we're dealing with. So this little tag up here is going to help us label. And we're going to label the A column as our X values, and then I'll just hit Tab. We're going to label our B column as our Y values. In C, we're going to be figuring out the value of the derivative at each step along the way. So I'm going to type that in as dy dx. If you put the slash in there, it doesn't like that. In fact, I'll show you, and it yells at you when you try to do that. So I'm just going to take out the slash and just leave it that way. And the D column, we don't really need a whole column for that, but that's going to be your delta x that's defined for you. In fact, as everything progresses, this 4th column of dx is the one that's going to remain constant. So if I look right here, it tells me that dx is always going to stay at 0.3. So in this row right beneath the label, we can go ahead and type in a 0.3, and it's going to populate that entire column as far down as we could ever want to go with a whole bunch of 0.3s. And that's good because, like we said, it was never changing. Okay, over here in cell A1, and remember everybody, right down here in the corner, it tells you what you're in, but of course you can see up here we're in column A and row 1. We're going to put in our initial x value, and if we go back to the ordered pair right over here, we can see that this thing began at the ordered pair -2, 3.4. So I'm going to type in -2 for my first x value, then hit tab, and my first y value was -3.4. I'm going to tab over into the dy dx column, just making sure that I've got everything right. And here's where things get just a little bit interesting. Now, what we're trying to find right here, which we're going to need in the next row to come up with our next ordered pair, is the value of our derivative, our differential equation, evaluated with these values of x and y, the previous point that we had. So for dy dx, we're going to type in a formula. It's going to begin with enter, and we defined our derivative earlier as f1 of x comma y. So we wanted to look for the x value here in cell A1, comma, and we wanted to look for the y value in cell B1. Now in this particular example, the derivative was only referencing the y value, which in this case is the negative 3.4. So that negative 2 isn't going to contribute anything here at all, but typing it this way leaves it a little bit more universal so that in the next problem, we don't have to retype that formula. So if I go ahead and hit enter, it gives me this messy decimal here of 1.8963 and so on and so forth. And what that is the slope of the tangent ray or the tangent line coming out of the ordered pair of negative 2, negative 3.4. So if we go back to the diagram that we looked at in class earlier today, what we basically just found was the slope of this blue line right over here, albeit in our example, that slope is negative this time. Okay, so back to the issue at hand right over here, and let's go back to the calculator. Now, what we're looking for are the x and y values that are going to get populated in these two columns right over here. And x is really easy to find. Every time our function jumps to the next iteration, the new x value is going to be found with a formula. So we begin with equals, and it starts with the previous x value, which is found in cell A1, and we're going to add to that this delta x value that we had right over here. Now I could go get that 0.3 out of any cell here in column D, but since I seem to be using a lot of ones, I'm going to use D1. So the next x value is going to come from adding this negative 2 with the 0.3 right over here, and that should get us negative 1.7, and it does. The hard part is coming right over here in y. And what we're going to be typing in this cell right here is the formula that we talked about in class right over here, everybody, at the bottom of this page here, where we were going to use this formula, which is kind of a mess, to find our next y value. The way we read this was to say that our next y value is equal to our previous y value plus the derivative evaluated at the previous ordered pair times your delta x value. So, looks easy, right? We're going to type that in right here. So the next y value is equal to the previous y value, which is found in the cell right above us. That's cell B1. And then we're going to add to that the value of the derivative evaluated at the ordered pair negative 2, negative 3.4, which is exactly the value that we computed right over here in cell C1. So our derivative then gets multiplied now by our delta x value, which can be found right over here in cell D1. So what's going on in this formula here, guys, is that our new y value is being found by taking our old y value plus the derivative at the last ordered pair multiplied by that constant delta x value of 0.3. And when we hit enter then, we get a new y value of negative 3.9688 and so on and so forth. As far as the dy dx, the formula that we typed in above in cell C1 is still valid. So what we're going to do now is copy and paste that by highlighting that cell and hitting Control C, then going down to where we want it and hitting Control V. Now remember, guys, I'm doing that on a computer keyboard, so I hold down Control as I hit C and V. But for you guys on your calculator, it's a one-finger operation. You hit Control and let it go, C and let it go to copy, then go down, Control and let it go, V and let it go to paste. And what we have right here, everybody, negative 1.7, negative 3.969, if we were rounding, that is our second ordered pair. Now that took a while to set up, but the beauty of doing it this way is that once we've done the work in a generic manner here in row 2, all we have to do now, everybody, is simply copy and paste moving down, and this is why 10 steps doesn't really take us any longer than 2 or 3. So I go over to cell A2 and highlight. I'm going to hold down Shift and go right twice and highlight these three cells. I'm going to hit Control C to copy. I'm going to hold down Shift and the down arrow a whole bunch of times. And I think I need to go to row 11 in order to do that. And then I'm going to hit Control V for paste. It always warns you about overwriting. Yep, we're okay with that. And what we ended up with here then, everybody, is a whole series of ordered pairs that mimic the shape of the solution curve, going all the way down to here. So if we take a look back at the original question, and I'm on the wrong page here, not here, right here, we were being asked to approximate the value of y of 1. So now that we have our calculator spreadsheet all worked out, we've got the value right here when x is 1 for y of approximately negative 24.293. So that's what we would go ahead and type in for our answer, everybody. Right down here, that y of 1, hang on, I've got the symbol somewhere here, that y of 1 is approximately equal to, and now I forgot already, negative 24.293. And there we go. That's going to be our answer to that particular problem. Now, in terms of is it actually right or not, that gets a little bit more difficult to check. So let me walk you through how we're going to play around with this just a little bit. The one thing that I really wanted to show you guys, and I'm really sad I'm not with you when we do, one of the cool things that the Inspire will do for you is it will take these 11 ordered pairs that we have right here, and it would do exactly what we would try to do by hand if we had the time. It'll plot them for us really quickly and easily. Now, to do that, and I don't think this is anything we've done before during the course of the year, we're going to have to add a new page to our document here. I should have said this earlier. For those of you using a Scratchpad, Scratchpad only does calculators and graph pages. It won't do lists and spreadsheets, and it won't do data and statistics, which is what we need next. That's part of the reason this all needs to be done in a document. So I'm going to hit Control and then my dock button to add a page. And we are going to go to number 5 right here, add data and statistics. And I have absolutely no idea what the calculator is doing right here to come up with this jumbled mess. But cool things happen when you start to mouse over to the bottom where it says click to add variable. And you'll notice right here, these are the headings of the 4 columns that we put in our spreadsheet. Well, naturally, we want the horizontal axis to be our x values. So we're going to click once on that, and those dots all seem to fall in line. Now, of course, it's just a straight line, and it's pretty boring. But when we go over here to the vertical axis, we, of course, want that to be all of our y values. And prepare to be dazzled, everybody, because when we click that, all of a sudden, everything kind of falls in line. And this is what our solution curve to this differential equation more or less looks like. Kind of looks like the right half of a downward opening parabola, or maybe the opposite of an exponential growth graph, something like that. It's kind of difficult to tell. The only thing we could really do to find out if we're right or not, and this is something I don't think I've shown you guys how to do yet, your Inspire will graph differential equations for you. I don't have a graph page open right now, so I'm going to hit Control, Document yet again, and now we're going to go to number 2, which is to add a graph page. Now you'll notice right up here that we're still on function mode, but what we're going to do instead, guys, is go to Menu, go to number 3, which is Graph Entry and Edit, and we are almost always doing functions. We messed around a little bit in the last chapter with relations, but for now, we're going to go all the way down to differential equations. And what is going on right here is that the first diffie-q we're graphing, the calculator is automatically calling y1 prime. And right here, you're going to type in the equation of your derivative. Now, we have it written as y minus the cube root of y. The one thing, and if you can't get a differential equation to graph, this is probably what you're doing wrong. Instead of just typing y, we have to type in y1 so the calculator knows that it's in reference to this differential equation here. So it was y1 minus, and then our next part was the cube root of, and again, instead of just y, it's going to be y1. As I think you can see what's happening right here, x naught, y1 naught, they're asking us for the initial condition. And this initial condition right here was the ordered pair of -2, -3.4. So I type in -2, tab, and -3.4. And when we hit enter, we get a slope field, including a solution curve passing through the one point that we were given. Now, I want you guys to notice this curve is completely contained here within the third quadrant, where it looks like x and y are always going to remain negative. Okay, and it does seem to be swimming with the current pretty well. If I go back to my data and statistics page, we see that the shape of this mimicked curve here and the shape of the solution curve here are roughly the same. Not exactly, but roughly. But we have to remember that both of these, both slope fields and Euler's method, are just ways of coming up with approximations to a solution. Neither one of them is going to be perfect, and they're not going to match each other perfectly. The big difference you'll notice is that this curve right here looks like it's contained completely within the third quadrant here. It doesn't necessarily look like it's maybe ever going to cross the x-axis, excuse me, the y-axis. There it does eventually if we go far enough down. This one right here crosses the y-axis pretty early at -12 and then spills over into the fourth quadrant. This one looks like it crosses maybe somewhere actually about in that same neighborhood of about -12. So actually those two are closer than I had thought right there. So all this stuff at the end, the graphing of the dots and the slope field, those aren't things that we really needed. As soon as we went to the table right here and found that when x was 1, our y value was approximately -24.293, we wrote that down right over here in our work, and we were pretty much done there. When we do eventually take a quiz or a test on this stuff, I'm probably not going to make you show a whole lot of work by hand there, and I'll allow you to just to give me that answer right there. It's a tough one to grade because there's not a whole lot of partial credit, but that's how that one is done. I think you can imagine that doing this problem this way, like we did in A, would have taken a lot longer. Okay, so that took some time. The good news is that once we have the method down, moving on to a new example like this really isn't going to be all that difficult, and it's not going to take us a ton of time. We need to change a few things. We need to change the original differential equation given to us right here, the initial condition, which in this case is -2, -4, and then our step value, which I've taken back to a 0.2. I can see right here that we're starting at an x value of -2, ending at an x value of +2. That's a total gap of 4, and we're taking a step size of 0.2. 0.2 is 1/5. 4 divided by that 1/5 means that it's going to take us 20 steps in order to do this. So we certainly wouldn't want to do it by hand. Let's go back to the calculator page. And the first thing I'm going to do, guys, remember that if you hit Control up, that shows you all of the pages that you have open right now. We're going to go back to the calculator page, and I'm going to redefine the same function that I named it before. So we're going to define f1, and again, of x comma y to equal, and in this case, our derivative is 6x minus 4x cubed plus y over 10. 6x minus 4x cubed, gotcha, plus a y over 10. Double check that one more time. Got it right. And that's all we need to do on this page. I'm now going to hit Control right arrow to move me back into the spreadsheet. Now my x column still is called x, but the initial x value, oh, this was dumb luck, is still -2. So that's good. Don't have to change that at all. If I did need to change it, let's just say to a +7, you'll notice that all of the other x values change as well. Okay, I just undid that. My initial y value in this problem is now -4, so we'll type that one in. The great thing about the derivative here is that the formula doesn't change. The formula still comes from evaluating f1 of x comma y by looking at cell A1 for the x value and B1 for the y value. So this doesn't need any work at all. The dx column is probably going to change from problem to problem, and right here we're back to a 0.2. Yes, I'm okay overwriting that, and everything has changed. That was pretty much it now, everybody. If you take a look, we started at the ordered pair -2, -4. We went up 0.2 units for our next x value to negative 1.8, and the y values came from the formula that we put in before using that value for the derivative. The only problem we're going to have is that in the previous problem, I think we needed to take 10 steps, and in this one, we said we needed to take 20. I didn't need to end this thing at y of 0. We were trying to find y of 2. So what we're now going to do is copy these 3 cells again in row 11, Control C, and then we're going to hit Shift and go down, I believe, to row 21 and hit Control V. And the hope would be then, everybody, that we are now going to know the value of y of 2, and that's happening right here. When x is 2, we get an approximate y value of 1.299. So we're going to go ahead and type that in right here, everybody. That y of 2, let's do it right. That y of 2 is approximately equal to positive 1.299. And that takes care of that, everybody. It is just that easy once you get your formula typed in. Now, I'm sure this question is going to come up like it has in the past. Yes, I'm okay with you guys using that formula in your calculator. No, you don't have to clear it out. And yeah, we're going to be fine there. Just to see what's happening, as soon as you do this, things moved around a lot. So I'm just going to go back here, and even though it said X already, if I hit X one more time, it kind of recenters things. I don't know that this is necessary, but I'm going to hit Y, and now this is a much more interesting solution curve than the last one we had. That one looks like a negative 4th degree function, if I had to guess. All right, and if I went one page further over to the right, oh boy, that's a mess. What if I went back to Menu, Window, and Zoom, and went back to Standard? Now, my initial condition is going to be wrong here, so let me go back and try. Oh, we didn't change the derivative either. So if I hit Tab, all right, let's change this derivative around here, and it was 6x minus 4x to the 3rd power, and then a plus y over 10. That's what it looked like. And our initial condition still started at negative 2, but our first x value was 4. And if we do that, I made the mistake that I told you guys not to make. Instead of a y, that needed to be a y1. And now when we hit enter, oh boy, we get this interesting looking shape here, and it didn't connect those dots for us. I'm not sure why that is. Let's clear this out because I'm in Y2 here, and that probably shouldn't be there. Nope, nothing wants to clear out right there. Okay. Okay, so everything looks pretty good right there. It didn't quite connect it the way that I wanted, but if I drag this down just a little bit, well, there it is kind of connected. We start to see a very similar shape right here, a negative 4th degree function that seems higher on the right peak than it is on the left, and that exact same thing happened right here. Not identical, but pretty darn close. Okay, everybody. So that was the fun part in 9.3, being able to use lists and spreadsheets and functions to be able to do all that work for us. All right, everybody. Hope it was fun for you. Everybody take care, and we'll talk to you at some point here. All right. Go Bears.